Hello there, thanks for joining. We're excited to have you. Today's session is Tame your Spring Microservices with GraphQL stitching using Lilo. And I hope you stick around because we're going to have a couple great demos showing you the capabilities of GraphQL and Spring. And also, I think you'll enjoy our Lilo and Stitch theming. About me, I'm Eric Murphy. I'm a software and cloud architect. Formerly worked at Solo.io and Red Hat. Been a Java developer my entire career, and more recently, deploying those Java applications to AWS and Kubernetes. Been a Spring developer since 2010, and I actually put a Spring Boot 1.0 application into production in 2014. Also published author, fan of GraphQL, and recently considered myself a Kotlin convert.
Hello everyone, I'm Fred, working as a software engineer, architect, tech lead, and consultant for more than 20 years, mostly working on Java, cloud, microservices, and software architectures. Contributed lots of open source projects and developed some of them from scratch. Lilo GraphQL stitching library is one of them. Unlike most of the backend developers, I like DevOps stuff and even front-end development. I also founded a couple of companies. Currently, I'm the founder of FreeAttack. I'm living in The Hague, the Netherlands.
So what are we actually going to talk about today? Well, first, I want to talk about REST versus GraphQL and what you need to know. It's very important to have those fundamentals in place. Also, why do REST microservices need to be tamed? What's so wild about them? Well, I'm going to talk about that. Additionally, I'm going to talk about how GraphQL stitching can tame those Spring microservices. After that, Farad's going to talk about his Lilo project, how it works, why it's awesome, and give a demo. Next, we're going to have another demo that's a little bit more advanced with an application that I built called Pictograph. I'm going to show you a specific use case for using GraphQL with Lilo, and also showcase some observability features of using GraphQL. And then Farad's going to talk about how to get started with Lilo and how you can get involved. Okay, REST versus GraphQL, what you need to know. So I really want to highlight here just how different REST and GraphQL are, even though they have overlapping functionality in providing API endpoints for your microservices. And you as a developer should really understand the differences between these two technologies so you can understand also the pros and cons of each technology, right? And so REST, it is very much dependent on the HTTP protocol, right? You have those HTTP verbs, you have HTTP error codes across multiple HTTP endpoints. REST is a very HTTP-centric specification that you can apply to your microservices. GraphQL, however, is transport agnostic. You can run it on HTTP or WebSocket or RSocket. And when using on HTTP, it comes through a single endpoint versus multiple endpoints. And there's only one verb that's really applicable here. It is a post request to that GraphQL endpoint. And as far as error handling goes, you're going to get your errors back as JSON data from that GraphQL endpoint. And it's going to have a 200 OK response code. Very, very different between REST and GraphQL. And then with caching in GraphQL, it's pretty much handled on the client side because that's where the queries are originating from the client. And each client is requesting a specific set of data from your GraphQL endpoint. So it makes sense to cache it on the client side. So next up, point 6 and 7 here, overfetching and underfetching. I'm going to cover that on an upcoming slide, but these are some challenges with REST versus GraphQL where with REST, you're returning potentially too much data back to a client, right? Where GraphQL, it can have clients query for exactly the data they need, right? And potentially do it across multiple endpoints. So moving on here, point 8, REST, it is weakly typed. GraphQL is strongly typed. That means if there's type errors for the queries and the data, that are coming into and out of your GraphQL microservices, that is going to generate errors. As far as schema goes, here, point 9, REST requires an open API / Swagger schema, where GraphQL has its own schema specification. And then points 10 through 12 here, I'm going to cover as well upcoming, but versioning of APIs is a real challenge with REST, where GraphQL is much more elegant in how you can evolve an API. So takeaway here for REST is it is really simple for small, simple APIs, right? Especially if these APIs are not really changing over time. But as you accrue a lot of different clients across multiple services for APIs that are changing and requiring multiple versions, it gets complicated very, very quickly with REST. Where GraphQL, the bar for getting started is a little bit higher, but generally speaking, the scalability on complexity is linear with GraphQL. GraphQL is better able to adapt to changing APIs across multiple services and serving up data for multiple different types of clients. So that's my comparison here between REST and GraphQL. So next, why do these wild Spring REST microservices need to be tamed? So let's take a look. So there are 3 main problems with Spring REST microservices, and this goes for pretty much any REST microservice, but these happen to be implemented in Spring, right? So the first problem, as I mentioned just a moment ago, is overfetching. That is where you're returning too much data in a single response back to a client. And so if you have a Spring REST service, it's going to return all fields that are in an object defined for your REST API. And a REST client will parse and deserialize the entire object that is returned from that REST API request. So this is a waste of resources for the client, for the server, and the network. So if you only had 3 out of 10 fields the client actually cared about, that is 70% wasted resources. So, for a single API call, that may not sound like a big deal, but if you're making thousands or hundreds of thousands or millions of API calls across a network with a high amount of latency, this adds up to be a major problem. The next problem here is point 2 is underfetching. This is where you're making multiple requests to retrieve the needed data from client to server. And so Spring REST clients, they'll actually often call multiple endpoints across these multiple services to get that data they need. But there is complexity in orchestrating multiple HTTP REST requests concurrently, or potentially even doing it sequentially, right? And so, in summary, overfetching and underfetching create a lot of waste, and they often happen together, and this creates a compound amount of waste, as we'll see in a demo later in this session. The last main problem here is API versions. This is where you have many different clients that require different versions of your API. So the evolution of your REST API must be managed through versions, in part because you can't expect REST clients to automatically adopt to new versions of APIs, right? They may be slow to adopt a new API. And so, unfortunately, you may be in a situation where you have to support 2 or 3 or maybe 4 versions of your API for pre-existing REST clients. Also, once you have API versions, you need to deploy those APIs and potentially deploy them as separate microservices, or figure out a way to make your microservice modular and support multiple versions of a single REST API in a single deployment. And also, API management tools may be needed to keep those API versions organized and ensure a smooth experience for your REST clients. Ultimately, especially in a large organization, API versioning and lifecycle management is complex and costly. So next, how GraphQL stitching can tame your Spring microservices. So, what is GraphQL stitching? More specifically, schema stitching. So the idea here is that if you take two or more GraphQL schemas and combine them together into one common GraphQL endpoint, you can have a stitched schema that is generated automatically from those pre-existing schemas. And this can happen through something called schema introspection, where you have a technology, a library, or a service that implements schema stitching. It will reach out, it'll introspect those schemas, and it'll automatically create a new virtualized schema that can be used. And these GraphQL schemas can be merged together in three different ways. First way is where you have simple merging, where there are no overlapping types inside of your GraphQL schemas. And those types are simply merged together easily into one schema. The next way is through linking. This is where you're able to take these GraphQL types and nest them inside of each other. And there's an example below where, let's say, for example, you have a query input where in blue you have title, and red you have bar, and underneath bar you have name in purple, right? So let's say you have a foo service and a bar service, and they both have their own GraphQL endpoints. You can actually have a link from the bar in the foo service that carries over to the bar in the bar service that returns the name, right? So this allows you to essentially nest data together across two GraphQL services, but from the client's perspective, it simply looks like one schema and one service, even though behind the scenes is actually two. And the last way to merge together schemas is through type merging. And so if you have two different GraphQL types across two different services, you can assign them essentially the same GraphQL type and just merge the fields together into one. So schema stitching is very dynamic and also very powerful and provides a lot of handy abstractions for, quite frankly, making GraphQL much more simple from the client perspective, even though behind the scenes you may have multiple GraphQL services involved. So what are some options for GraphQL stitching? And this is not a comprehensive list. So first up is a dedicated GraphQL server, and Apollo is a very popular one, if not the most popular. However, Apollo is generally a proponent of something called GraphQL Federation instead of GraphQL stitching. And this is where you have GraphQL Federation and it's a composition of smaller GraphQL schemas. So this is similar but different than stitching, right? And I would say that GraphQL Federation, it's fine, but it fits better in the context of a fully fledged GraphQL server. Another option for GraphQL stitching is through a GraphQL-enabled proxy. And the best example is Glue from Solo, my former employer. And what they did is they actually added GraphQL capabilities to the Envoy proxy, including GraphQL stitching capabilities. So you can stitch data from client to service or even inside of a service mesh for service-to-service GraphQL calls. So this is a great option if you're running on Kubernetes and you're running Istio service mesh, you have an integrated GraphQL schema stitching capability. But more pertinent to this conversation is having a GraphQL stitching library, and for Java, there's two that are well known here. So we have Atlassian, Braid, and then we also have Lilo, which is inspired from Braid. So takeaway here is that libraries allow you to essentially build your own GraphQL stitching gateway and tune it to your needs. You're not dependent on a dedicated GraphQL server. You're not dependent on a GraphQL enabled proxy. You can kind of roll your own solution, which does have some benefits. So let's look at an example here of how you can avoid those three problems: overfetching, underfetching, and API versioning. So the first scenario here is that you have a REST API and there is underfetching and overfetching involved. And a specific example here is on the left, you have a client that says, hey, I need B, H, I, and K. I only need those attributes out of the REST APIs, right? But unfortunately, B, H, I, and K are available across three different services, right? So in order for that REST client to consume B, H, I, and K, there has to be three service calls made. And unfortunately, these service calls are going to return a ton of data that, quite frankly, is not necessary. As you can see here, there's a call 1, call 2, and call 3 to these three different services. So in this scenario, only 4 out of those 11 fields are actually needed, and there's 3 REST API calls from the client, which results in additional latency as a side effect. So what's the solution here? So you can actually use GraphQL stitching to eliminate over and under fetching. So if you have a GraphQL client rather than a REST client that says, hey, I need B, H, I, and K, that client can query specifically for B, H, I, and K and eliminate that overfetching and underfetching. And this query goes through the GraphQL gateway, which implements the GraphQL stitching capabilities. So it can send very narrow queries down to the services that actually contain this data. So for query 1, it would only query for B. Query 2, only query for H. Query 3, only query for I and K, right? So only 4 of those fields are needed and returned, and you have one GraphQL query from the client to the gateway. You have reduced latency there from client to gateway, and that GraphQL stitching is key to this solution. So next, let's look at REST API versioning to support multiple clients. And let's say you have 2 different clients here. One needs B, H, I, and K. The other one needs B, H, Z, and K. So there's a difference there, I versus Z, right? The API has changed, it's evolved, right? So once again, each of these clients needs to make 3 different calls in order to obtain the data from the REST services, right? And for the client requiring Z, it has to call essentially a version 2 of the service 3, while the first client will simply continue to call the version 1, right? So as you can see, just from the picture, this becomes quite complicated, right? Where you have 2 versions of your service 3, you have all these calls happening, a lot of data crossing the wire that, quite frankly, isn't needed. There's no way to deprecate fields. And so you have to have the API lifecycle management in place in order to make sure that your APIs are stable and serving up the needs of these particular clients. So with GraphQL, you actually can evolve your schema and you can deprecate fields that are returned from your queries, right? So it becomes easier to support clients that need different data and different versions of data, essentially, right? So if you have a client that needs both I and another client that needs Z, you can support that through a single GraphQL endpoint, right? And so this is very powerful in comparison to REST and having the API lifecycle management complexities. And once again, in this solution, GraphQL stitching is still in play. So next we're going to move on to Frat and talk a little bit more about the Lilo project.
Alright, Lilo. Yes, Lilo is a GraphQL stitching library. Basically, it stitches remote or locally defined schemas together. And when it does its job, it does quickly, mostly because it's very lightweight and we also try to keep the number of external dependencies low. It's framework independent. You can use it with any numbers of Java web frameworks or even basic Java servlets. We have provided plenty of Spring Boot 3 examples in the code base. Today, we are gonna show a very basic example of Spring Boot 3 as well. We constantly check the code base and dependencies against vulnerabilities. Our releasing period is quite often. According to our release timeline, for some months we have released more than 3 releases. Lilo is easy to use and we are trying to make it even more user-friendly. It's possible to integrate Lilo into your project with just few lines of code. Let's talk about what Lilo actually does. If you are using Lilo on an API gateway or reverse proxy level, you can easily combine many GraphQL schemas together. As shown in the diagram, Lilo works as an interceptor and checks all incoming requests and then dispatches the queries and mutations to their respective microservices. Then combines or stitches the response coming from microservices. The communication is mostly over HTTP, but for microservices part, it's possible to use other types of protocols such as gRPC, RSocket, or even message queues. Sky is the limit. Also, not just for remote schema sources, Lilo can work with locally defined schemas. Let's take a deep look into how Lilo works. Well, in this example, we are gonna use 4 basic meta operations as GraphQL queries. Add and subtract. Meta operations are served in microservice A. Multiply and divide meta operations are provided by microservice B. So Lilo initially sends an introspection GraphQL query to those attached microservices. Introspection query helps to fetch all defined queries and mutations in that microservice. Lilo achieves these fetching operations using an implemented introspection retriever class. So, after fetching all defined queries and mutations from microservices, it creates an internal map or dictionary to associate queries with microservices. For this specific example, add and subtract queries are associated with A, and multiply and divide meta operations queries are associated with B. When a GraphQL request arrives, Lilo starts analyzing the incoming query. In this example, we have 4 different mathematical operations. We could use the same mathematical functions with different or the same parameters using aliases. But let's keep the example simple. Okay, we have 4 different meta operations inside one query statement. Lilo checks every single query and mutation, then tries to associate queries with microservices by looking up its internal dictionary. After that, Lilo knows which query retriever class will be used to get a response from specific meta operations. As a next step, Lilo used defined custom query retriever for a specific microservice and sends the associated queries. Then sends it to the next microservice. Microservice A executes the queries and returns the responses, and same for microservice B. Lilo combines all incoming responses and generates a common response for query as if it's one query and one response. Under the hood, Lilo uses some caching and lazy fetching for performance benefits. Okay, we are gonna create a very basic Lilo gateway project. It will be a multi-module Maven project, and we are gonna create 2 microservices, basic microservices, and 1 gateway with Lilo gateway. Okay, let's create an empty Maven project. Let's name it Lilo basic example. So okay, our project is almost ready. I'm gonna change this POM XML file. So currently its packaging is jar, so I'm gonna change it to POM because it will be our parent POM file, and delete source directory, not gonna need that one. Okay, and I'm gonna create one more module for Spring Initializer. It will be a server 1, and Java Maven is enough. For server 1, I need a server and also GraphQL capabilities of Spring Boot. So our server 2 is pretty much identical to server 1. Server 2, Java Maven, and Spring Web, also GraphQL. Okay, one module left. I'm gonna create a Lilo gateway. Gateway module, Java Maven. So web is enough for that one because we're gonna use Lilo gateway library, and so it will stitch and dispatch the request. Okay, yes. Let's modify first our server 1 application. I'm gonna create a hello controller for defining our query. It will be controller, and I need a public method. It can be hello1. So, and say query mapping for GraphQL mapping, and it will return, let's say, hello from server 1. Okay, but this definition is, I guess, not enough, so I need to create a type definition file here, schema GraphQL schema file. So let's say type and query hello1 string. Okay, so one more thing, I'll adjust the server port from 8080 to 8081. Let's say use services, and then run server 1 application. Let's try what will happen. Okay, so let's use curl to test the application. I will send an hello1 query to localhost 8081 GraphQL nodes, and okay, our server 1 is running. Let's do the same thing with server 2. I'm gonna copy this one and paste it to server 2, but need to change the method name hello2 and hello from server 2. Okay, let's copy the other stuff as well. Schema GraphQLs file. Okay, let's change this one also, and application properties server port 8082. Okay, so let's run the server 2 application. Okay, our server 2 application is running, and I'm gonna test using curl Let's change hello1 to hello2 query, and the port number is 8082. Okay, this one also works. So the last part, I need to modify my gateway. First, maybe it's better to define the Lilo dependency. So Lilo dependency io.via, and Lilo version is currently, the latest version is 23, or which means April and 2. Let's refresh our Maven project. It should be okay. And I need to create one controller class, Lilo gateway controller. Okay, let's annotate with this controller, and I need to create a public method, and let's say, okay, map string object, it will return map basically, and I can name it, I don't know, stitch. So this will be our GraphQL endpoint. So, but I need to create the Lilo instance. I can create it inside this method, or I can use a constructor for if I use constructor, so it's better to, because it's one-time instance, it will be one-time instance, and inside the singleton, that makes more sense. Okay, let's say this will be Lilo, and using Lilo builder at source, remote schema source, because microservices are remote schema sources, and create. So let's say it will be server 1, and so here we need to provide the schema endpoint, localhost 8081, and GraphQL. In general, GraphQL endpoints are mostly GraphQL. So let's create it for server 2, and done. Let's initialize this one. Okay, for the stitch method. Okay, we are going to use this Lilo instance inside this method, but first of all, yeah, it will be a response body, because we need map as a JSON object, and post mapping for GraphQL. Okay, and what else? We need a request body, so the incoming object will be a GraphQL request. Let's annotate with request body and GraphQL request. Let's say it will be request, and we are going to return the response of the stitching operation. Request. So request has built-in method to an execution input. So it's easy to just provide execution input the parameter of stitch method, and for execution result we can directly convert to a specification which provides a map, and I guess that's all. Yes, I need to run the gateway application. Okay, now it's running. So let's try. Okay, I sent hello1 to 8081, hello2 to 8082, and I need to send both of them hello 1 and hello 2 to 8080. Okay. Yeah, as we can see, GraphQL stitching works fine, and hello 1 request dispatched to the microservice 1, and hello 2 routed to microservice 2. Yeah, that's pretty much of it. Little roadmap. One of the most wanted feature is namespace and linking support, which makes a lot of sense. I guess we can implement it in very short period of time. It's priority one. Then the next most wanted feature is GraphQL stream support, so developers can use end-to-end dynamic stream responses. It will be easy to get events in pops-up manner. So for the midterm goals, currently we are using one retrieve operation for every single query and mutation internally. Most of the use cases are high-speed microservice communication in data center or Kubernetes, but if the intent is the stitching the external third-party microservices or third-party services, GraphQL services, it might cause a small amount of delay depending on the number of queries. The goal is grouping the queries per schema so we can reduce the count of trips, less response fetching, but it will be configurable. In some scenarios, parallel fetching might be faster than one big group of sequential fetching. One of our users were using a dynamic GraphQL schema creation system. It was kinda a backend as a service system. So some specific mutations were creating other kind of queries and mutations. In current situation, cache invalidation works perfectly, but in the future, we might work on an optimized cache invalidation for such scenarios for speeding up the introspection time. Also, we consider to create an additional Spring integration dependency to make it possible to create annotation-based retrievers, which makes it easier to create and modify retrievers. Another fantastic feature is developing a standalone Lilo GraphQL stitching gateway, so developers can configure the gateway with its internal GraphQL API or a configuration file.
Thank you, Rod, for that great overview of the Lilo project. So next, let's move on to Pictograph, which is a Spring GraphQL and Lilo demo application. And the goal of the application is to show a little bit more advanced capabilities. So the idea with Pictograph is it has an API that mimics a photo sharing website. So this is a website where you have users, and the users are sharing pictures, and they have the ability to like pictures and post comments. So that type of capability, right? And with this demo application, we can demonstrate three different scenarios where, first of all, we want to prevent overfetching and underfetching of data using GraphQL stitching. So I'm going to demonstrate that. Also, I'm going to demonstrate two forms of observability with GraphQL, one being distributed tracing and the other one being tracing instrumentation. So I'm not going to have time to go into everything about this demo application, but I highly encourage you to check it out. It's out on GitHub at murphy/Tame Spring Microservices GraphQL. The application, it is written in Kotlin. It's completely reactive Spring Boot 3. So next I want to show you the architecture of Pictograph. So here is the dependency graph in the Zipkin application. And we're going to come back to Zipkin later because we want to see some distributed traces. And we can see that through the Zipkin application in case you've never used it. But here it's actually showing a graph showing the service calls from the Pictograph gateway here on the left over to the other three services, the like service, the user service, and the pick service. So these are all the GraphQL calls that are happening from Lilo outside the gateway. So next I'd like to jump over to IntelliJ and just walk through the implementation with you. So first I want to show the pick service and show you the actual GraphQL implementation. So there's a GraphQL schema here for pick. So you can see we have a pick type, pick ID, user ID, pick URL, pick comment. And also there's 3 different queries: picks, pick, and picks by user ID. And if we look at the actual pick controller, you can see that there is query mapping and functions for pick, picks, pick, and picks by user ID. So those align to the actual queries defined in the GraphQL schema. So in this case, there's simply hard-coded data from a list. And so, for example, there's a picture here that was added by me. And you can see the URL, and you can see a comment that I posted. Check out my view of Mount Rainier, right? So a very simple GraphQL service. The user service and the like service are implemented in a similar way, just a very straightforward GraphQL microservice. So next I want to go over to the pictograph gateway implementation. I'm going to pull up the gateway controller here. And so this will be similar to what Farhat showed in his demo, except for this is in Kotlin. And in this case, I have the GraphQL post mapping endpoint. I'm getting the GraphQL request in the request body, and I'm passing that request off to Lilo, where it's performing the stitching actions. So same basic functionality. The difference here is I'm actually injecting an instance of Lilo. And if I go look at this Lilo configuration, I'm actually creating a Lilo bean. And I'm using some application properties values to construct the Lilo object, just simply making it more configurable. And if I look at the application properties here, I can see the GraphQL endpoints that are available. I can see that I'm setting up distributed tracing as well for Zipkin. So you can see a Zipkin endpoint here. And I'm also enabling some instrumentation as well for Lilo, which we'll discuss later. So simply making Lilo a little bit more configurable here for the different GraphQL endpoints. So next I'm going to go over to the pictograph gateway README, and I'm going to talk about the scenario where it shows how we can prevent the underfetching, overfetching problem. So let's pretend we have a scenario where we want to create a user profile page for Pictograph. And on this user profile page, we want to show basic user information. We want to show what pictures that user posted, and also what pictures were liked by that user. So just a very limited set of data that we want to show. And if you were to implement this using REST microservices, you might have to make 3 separate service calls: one to the user microservice, one to likes, and one to pics, right? All through the REST APIs. So you're making multiple calls. In addition, each of those calls you might get extra data back that you don't care about when you're implementing the user profile page. So in this case here, I actually have one GraphQL query that is getting only the relevant user data, only the relevant pick data, and the relevant like data, right? Nothing more, nothing less. And the beauty of this is one GraphQL query, and this is one call that needs to be made. In this case, I'm using curl, right? So I'm using a curl post here, and I'm posting this query out to the pictograph gateway, GraphQL endpoint, and I am passing in these variables here as well. So the variable here is user ID Murphy, and this curl command will execute, and you'll get the JSON data back. So for readability, I already have a sample response back here, and you can see in this single result, I'm getting back only the relevant user information, the pix information, and the relevant likes information, all in one single response. So that's pretty nifty how that can work, and this really demonstrates how it simplifies things from a client perspective, where they're only having to make one query to the GraphQL endpoint to get data from essentially 3 different services, right? But it's completely invisible to the client, and that's a good thing. So next I want to jump over to Zipkin and talk about distributed tracing. So I'm going to go over here to find a trace, run a query. So what you're seeing here is different traces with different trace IDs, right? And the way it works with distributed tracing, you have a trace ID that's generated when you have an incoming request into the pictograph gateway. So we have this trace ID, and it's propagated to the backing services, which in this case are user service, like service, and pick service. And if I click into one of these, you can see the associated spans for that trace ID. And you can see the top level pictograph gateway HTTP post. And then you can see the underlying user service HTTP post to the GraphQL endpoint. But what's cool about this is you get additional spans that show you the underlying query executions for GraphQL. So you can see here that in the user service, the query execution took about 38 milliseconds. And the underlying piece of the query related to pulling the user data out took about 14 milliseconds, right? So we're able to go a level deeper here into the actual application execution with these distributed traces. And that's really valuable if you need to identify bottlenecks, if you have slow queries potentially. You're able to identify those very easily, even if they're running in production, right? You're going to have these traces available and be able to identify what the problem is and hopefully fix it very quickly. And if you need more granularity on traces with your GraphQL queries, the other implementation that I have in place is in the Lilo configuration. I'm going to go back here and look at the builder object for Lilo. I'm actually setting a tracing instrumentation object. And this object is available from the GraphQL Java library. And once you add this instrumentation in, you're going to get extra results back in your GraphQL responses. So if I go back here to the README, I can see this is the response with the data that we were just looking at. But also there's extensions as part of the response, and you see this tracing data. And this gives you a more granular view on what is executing for the GraphQL resolvers. And you can see that there's likes by user ID, there's picks by user ID. So you can see all the queries and executions that are running here, right? And you can see the return types and field names and the duration of execution. So this allows you to go another level deeper into identifying where there might be potential problems with your queries, potential bottlenecks. So hopefully you find this helpful as far as understanding what's available for improving observability with Spring GraphQL microservices and how that could be used with Lilo for distributed tracing to get the end-to-end visibility for your GraphQL microservices. And then, of course, as we mentioned, preventing overfetching and underfetching of data using GraphQL stitching. So next I'm going to pass it on to Farhat, and he's going to talk about what your next step should be for Lilo.
All right, let's talk about how we can bootstrap a graphical stitching system as fast as possible. So integration Lilo into your project is just one Maven dependency. The dependency is in the central Maven repository. So you don't need to add an external Maven repository definition in your build system, in your Maven file or Gradle file. So you can always check the latest published release from GitHub link or from Maven Central repository. For standard configuration, if no authentication or any kind of header or payload manipulation is needed, it's pretty easy to configure. A couple of lines are enough. For advanced configuration, so we are trying to provide lots of samples for different scenarios. It's always good to check samples directory in codebase. For GitHub repository, I personally want to move it to an independent Lilo GitHub organization under a different top-level domain, something like org.lilo or something. After a certain amount of GitHub stars and usage stats, it might be better to provide it from a different domain. So how can we contribute to Lilo? Well, of course, by using it. If you found any issues or you have some sort of feature request in your mind, don't hesitate to create issues, or you can directly create pull requests for your new ideas, bugs, or basic type of fixes. Also, it would be perfect to have more blog posts about Lilo. Currently, there are few on the internet, and they help a lot to people bootstrap their projects. Another contribution is helping the documentation of Lilo. As you can notice, I'm not a native English speaker, so typo or grammar mistake fixes would be much appreciated. Thanks everyone for listening. If you have any questions, please don't hesitate to reach us out. I personally want to thank everyone who is interested in GraphQL teaching and especially Lilo project. Now I want to thank Eric. Without him, this presentation would not be possible. Also, special thanks to Spring One and VMware for providing us such a great platform.